Working with raw binary data can feel like sifting through a mountain of ones and zeros, especially when you need to structure and manipulate it. This lesson will show how Elixir turns intimidating low-level data into powerful, pattern-matchable structure called a bitstring, giving you a clear, functional way to handle complex formats. Dive into the Paint by Numbers exercise with me to discover how to use binary pattern matching to easily prepend, extract, and drop data segments.
All right, welcome. Today, we're going to tackle one of Elixir's most powerful and, let's be honest, kind of intimidating features. We're talking about bitstrings. And we're going to go from feeling a bit lost to totally confident, all thanks to a really cool paint by number exercise from Exercism.
Howdy, I'm Kevin. In these videos, I explore AI tools to help us learn. For example, I use NotebookLM to explain concepts and Copilot to autocomplete and automate for efficiency. I balance AI with my experience as a senior dev to show how to solve the exercise and to keep AI honest. Watch this video for a comprehensive presentation of the exercise and the Elixir concepts, and of course, also for my solution.
Okay, tool number one is the bitstring literal. You'll see it with these double angle brackets. Seriously, just think of this as your color palette. It's Elixir's super elegant way of building binary data piece by piece, letting you say exactly what value goes in and exactly how many bits it should take up. And our second tool, pattern matching. This is how we take that data apart. And it's so much more than just checking if things are equal. It's about elegantly deconstructing them. That ... bitstring specifier you see, that's our secret weapon. It's like having a magic tool that can lift one specific color right off the canvas without disturbing anything else.
I have downloaded the Exercism Paint by Number exercise and loaded it into VS Code. I've also run our Generate Docs prompt in Copilot, which grabs the information out of the README, test file, hints file, and adds function documentation so that we can more readily refer to it here rather than jumping back and forth between this and the README.
So step one is a really crucial one. We need to implement palette bit size. And here's the puzzle. How do you figure out the minimum number of bits you need to represent all your colors when you don't have the normal math functions you might be looking for? Yeah, the tricky part here is Elixir doesn't just hand you a log2 function. So what's the Elixir way to solve this? Recursion. It's actually pretty clever. We just keep doubling our bit capacity until it's big enough. So if you have, say, 13 colors, 3 bits only gets you 8 combinations. Not going to work. But 4 bits, that gives you 16. Perfect. So now that we know how big each pixel needs to be, we're ready to create our canvas.
You might be tempted to change the arity of this palette bit size to pass the number of bits around so that we could recurse on it. But Exercism doesn't really want you changing the signature of these public functions, so we'll declare our own. Let's call it calculate bit size. Okay, let's see here. This is backwards. So what this is going to do is take the color count and the number of bits we're considering, and if 2 to the power of bits is bigger than the color count, then we have enough bits to store that color and we'll return it. Otherwise, we need to try the next number of bits up from there, and we'll keep doing this until we get a large enough bit size. And then here we can call calculate bit size, and we need to pass in the color count, and we'll start with 1. Think of a bit string like a modular, custom-built Lego chain where each piece or segment snaps together. You get to define the exact size of each piece, and then you use Elixir's binary syntax to snap a new piece onto the front or identify and detach the first piece without touching the rest of the chain.
Okay, every masterpiece needs a blank canvas to start with, right? So our next function, empty_picture, has a simple but super important job. How do we represent nothing when we're talking about bitstrings? And the answer is just beautifully simple. It's an empty bitstring literal.
As involved as calculating the bit size might have been, empty picture couldn't be any easier. They simply want us to return an empty bitstring, which is double less than, double greater than. I'm always refining the content based on the ever-changing AI landscape. What AI content did you like in this video? What AI feature would you like to see me use in a future video? Let me know in the comments.
All right, next up, we need to build a test picture. I mean, how are we going to know if our other functions work if we don't have a simple, predictable little image to test them on? So this step is all about building a known binary structure from the ground up.
The third instruction is to give you just a bit of practice defining a bit string. They want you to return 0, 1, 2, 3 from the test picture function. And rather than watch me type that, I will just take the autocomplete.
Okay, now it's time to actually put some paint on the canvas. We're implementing prepend pixel, which needs to add a new color to the front of our picture. And this brings up a really common challenge you'll face with binary data. Think about it. How do you add something to the beginning of a data structure when you have no idea how big that structure is? It could be huge. This is where Elixir's design is just brilliant.
Step 4 is prepending a pixel onto a picture. And they give us the picture, they give us the color count, and they give us the color to put first. And so the first thing we will need to do is figure out the size that we need to store our color with, and we will reuse our function from the first step is to get the palette bit size. Then, well, sure, we'll just take that Copilot, thank you. So then we say, let's take the color of type. So this is the size, the number of bits that this color pixel will be encoded with. And then add the picture with Bitstring is whatever length it is. One note is you could, in this case, put palette bit size straight into here when creating or encoding data. As you'll see in a minute, we can't do that when pattern matching. So that's why I went with this pattern.
Okay, so we've put a pixel on the front. Now we need a way to get it back off, right? That's what get first pixel is for. But it has to be safe. What should happen if we try to get a pixel from an empty picture? This is where we see the classic idiomatic Elixir solution, multiple function heads. It's beautiful. One version of the function is designed to match a picture that has a pixel at the front. It uses that kick pixel size _rest bitstring pattern to grab it. Then a second version of the function matches only on an empty bitstring, kick, and it just returns nil. No messy if statements, it's so clean and declarative.
The fifth instruction is pattern matching to get the first pixel out of the picture. And you'll see this looks quite a bit like getting the head versus the tail in a list. There's an extra note here that when given an empty picture, it should return nil. So over in our source code, let's handle that one first. Let's say when the picture is nil, empty, we don't care what the color count is, we're going to return nil. Then we can do our pattern matching. You'll also remember a moment ago that I said we had to calculate the bit size first in order for the pattern match to work. So here we are calculating our bit size. This is the function we wrote, instruction number 1. Then what we say is we want you to bind the first thing of this many bits to the variable pixel. We can ignore the rest. We need to bind to it, but we can ignore it. We don't need that value. So pattern match this to picture and then return pixel.
All right, next up is drop first pixel. The job here is to do the opposite of what we just did. We want to remove the first pixel and just get the rest of the picture. And if you're thinking the solution is going to look familiar, you are absolutely right. We use that same pattern matching superpower again. We break the picture down into the first pixel and the rest. But this time, we just return the rest. And of course, just like before, we have another function head to handle the empty picture case. It just returns an empty picture. It's perfectly consistent and easy to follow.
Dropping the first pixel is kind of like the opposite of getting the first one that we did just a moment ago. There is a clause that if it says here, drop a pixel from an empty picture, that we want to just return the empty picture. So let's do that. Then here, we're going to want to get our bit size. We're going to want a pattern match, but this time we want the rest of the picture. We don't care about the first pixel, so we have our underscore here to say bind to the first thing of this many bits, but ignore it. Then I want the rest, and we'll return the rest.
Okay, for our last big move, we need to implement Concat Pictures. The challenge is pretty straightforward. Take 2 separate pictures, and they could be any size at all, and stitch them together into one big canvas. And oh man, this is where the syntax is just amazing. It's literally one line. You just put them both inside a Bitstring literal and tell Elixir they are both of type ... Bitstring. That's it. Elixir handles everything, joining them into a brand new Bitstring. It's so clean, so readable, and crazy efficient.
And finally, concatenating pictures. This is simple. So long as you know the syntax, it's very simple. It's take whatever's in the first picture of variable length, I don't care, followed by whatever's in the second picture by variable length, I don't care, and return that as a new Bitstring.
So let's wrap this all up. What you've really learned here isn't just how to manipulate bits. It's much bigger than that. You've learned the Elixir way of solving problems. You're using the triple case syntax to build and deconstruct data. You're using pattern matching and multiple function heads to handle all your different cases and edge cases with total elegance. And you're comfortable reaching for recursion when you need it. This is what writing idiomatic Elixir feels like.
So the exercise made a big deal over being able to have a smiley with color indices. Like this was a old school bitmap image. So the image is made up of 3 colors. 0 is white, 1 is black, and 2 is yellow, but then didn't do anything with this bitstream. So I did. So here is our smiley bitstring. This is the 0s, 1s, and 2s that make up that smiley. And I made a function for render, which takes that smiley bitstring and calls a recursive render function. The render function says, let's just focus on this bit right here. We're going to pattern match our first pixel, the rest of the picture, and what column we're on. We're going to write that pixel. If we've gotten to 15 columns, we're going to put a new line. I threw the sleep in so you can just see it render and see the recursiveness happen. And then we're going to render the rest of the picture with the next column over. Just for completeness, to write a pixel, I'm using the ANSI IO to set the background color with 2 spaces, and then we reset our background color. And then here's the logic that says, well, if the column is 14 because it's 0 based, then put a new line, otherwise don't do anything. So here you go. Ta-da! Mixing and matching sizes in bitstrings provides fine-grained, memory-efficient control over binary data, ideal for parsing and constructing formats like network packets or images. Bitstrings integrate seamlessly with pattern matching, making binary parsing declarative and safe. Hit the like button. It's the perfect bit size to let YouTube know you enjoyed the video. Set up your learning by pattern matching subscribe. Dive into the playlist to continue building your expertise one powerful function at a time. See you there.